So today is January 23rd, and this is our third meeting, and we're going to talk today about some probability things that hopefully you'll find interesting and will be fun and interactive. And but before we get to that, let's ask if there are any homework questions. So we have homework 2, and I'm going to be writing with my finger, so forgive me for if you have trouble reading it.
Yes, number 6 is 12.
Number 6 and 12. Any other homework questions? Only one person's done the homework so far, probably. I might also, depending on how much time those other ones take, look at problem number 14. Okay, so let's go over here and go to assignments, homework. Homework 2. This. Yeah. Oh, from chapter 5 for the homework that's due not this week, but you're way advanced. Okay. You know, I think we should hold off on that for now. So next week you'll have a chance to ask questions about chapter 5 homework. So let's focus on homework 2 at this point. Question 8. So we're still homework 2 now?
Yeah.
Question 8 and 11. Okay, so let's look at 8 first. And 13. Someone said 13? Did someone say 13? No? Okay. All right. During a rock concert, the noise level in decibels, the front row seats has a mean of 85 decibels with a standard deviation of 12 decibels. Without assuming a normal distribution, find the minimum percentage of noise level readings within 17 standard deviations of the mean. That's the question. So, what do we know here? We know the mean, mu, is equal to 85. And we know the standard deviation, sigma, is equal to 12. We're told not to use a normal distribution on this. Why do you think we're told not to use a normal distribution? Well, because the data is not normal, first of all. But why is normal a bad option for this type of data? Anybody know anything about the scale for decibels? It's on a log scale, that's right. So to go from 85 to 97 is a big deal. It's not just 12 units louder, it's actually 12 times louder, basically. All right, so so logarithm means we're talking about the exponent, so some number to the exponent of decibels, and so we're just looking at just the exponent. Okay, so they want to know what is the minimum percentage of noise level readings within 17 standard deviations of the mean. So we want to be plus or minus 17 standard deviations of the mean. And so this is kind of it's a good question, but 17 standard deviations is huge, whether your data is normal or not normal. And in fact, if you went minus 17 standard deviations, what would the exponent be? It would be negative, right? which is okay because we're talking about exponents still. So decibel levels can go below 0, but that's saying 17 times 12 decibels below the mean, or 17 times 12 decibels above the mean, which is very big. So what are we going to use for this question? We're going to use Chebyshev's, and I don't know how to spell it, so I'll just use chicken scratch. The Chebyshev's theorem says 100 times 1 minus 1 over k squared percent of the data is going to be within plus or minus k standard deviations. So 17 is our standard deviation, so we plug in 100 times 1 minus 1 over 17 squared, and that's the percentage, which is 99.7. 99.7%. So if I just want to plug it in my calculator, I can do that. If I want to use Excel, I can pull up Excel and so we have so here's K. In this case, we have 17, and so lower limit is going to be equal to 100 times 1 minus 1 divided by k squared. So 99.63. I don't know if they ask us to round or not, but let's just not round and check our work. And so there we have it. If we were using the standard or the normal distribution, the results would be, you'd have to say 100%, because 17 standard deviations on a normal random variable are so far out in the tail that calculators and computers probably couldn't even. Well, let's just see if what we get. Norm dot s dot dist. Let's put in negative 17, 1. So there you have it. 4 times 10 to the minus 65. So we would be looking at 1. I guess 1 minus that. So, or 1 minus twice that. Really good. But rounds to 1 either way. Okay, so that's problem number 8. Let's look at number 11 then. Sorry, so was the question answered? We're good on that now? Who's working on that one? All right, number 11. Below are the monthly rents paid by 30 students who live off campus. Using Excel, find the mean, median, mode, and standard deviation. So what was the question on this one?
Just how do you get the standard deviation using Excel?
Okay, great. So we're going to click on the data set and download it. And so here's the data, and to get let me just copy this whole thing over to the other. So this is homework 2.11. Paste that in there. And this one is homework 2.8. So to get the mean, we're going to do something to get the median and STGEV, standard deviation. Right, they're asking for all these things, and oh, the mode as well. But let's just go ahead and the question is about the standard deviation. So to get the standard deviation, there's a formula that we can use. So this is homework 2.11. To get the standard deviation S, which is the sample standard deviation, we're going to take the square root of the summation of xi minus x bar, quantity squared divided by n minus 1. So we could just plug into this formula. How do we do this? So this is the sample standard deviation. Right, the standard deviation measures how far on average each individual data point is from the mean. Well, it's not actually the distance, but it's the squared distance. So if I take xi, so this is the first, take the first observation, subtract from that the mean, square that. Let's just write it out like this. So we have x1 minus x bar, quantity squared, plus x2 minus x bar, quantity squared. And we're going to do that for all of the observations. And then we're going to divide by n minus 1. And then take the square root. So could you do this with your calculator? Sure. Is it a pain in the neck to do with the calculator? Yeah. You don't want to do it with the calculator. The formula, however, is built into Excel, and you don't need to actually calculate the mean first. All you have to do is type stdev.s. That's the sample standard deviation. If you put .p, that will give you the population standard deviation, and the difference is for sigma, it's the square root of the summation of xi minus mu squared divided by n. So the only difference in the formulas as far as Excel is concerned is the denominator. So for the population, divide by n. For the sample, divide by n minus 1. So we're going to use the sample, and then all we have to do is put the data in. So all that data right there, say enter, and we get a standard deviation of 114.28. So let's just throw that in and check it out to see if we got it right. It looks like we did. Now they told me to round to 2 decimal places. I didn't. If in doubt, follow the rounding rules. And I'll show you another problem here in just a second where you can run into real trouble if you don't do that. Okay, so are we good on standard deviation? Okay, if not, come see me during the break or after office hours, and we can talk more about it. All right. Okay, so let's look at homework 2.14. Okay, so for number 14, we have a table that shows the distribution of winning times for the Kentucky Derby, which is a horse race, and this happened over 84 years, and you totally know that this is fake data because why? We have 93 observations. So they don't run the race more than once a year, so there's fake data here. And I guess it's good that it's fake because, I don't know, it's good that it's fake, but the way that we are given the data is not the actual values of X. Instead, we have the data kind of summarized, And you can think of this as a frequency distribution. So if you have a frequency distribution, sometimes you need to estimate the mean and the standard deviation and so forth, right? And oftentimes you do just get a frequency distribution. You don't get all the data. So instead of getting 93 observations, they gave us, how many are here? It looks like 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different frequencies, or 9 different bins. So you could make a histogram out of this if you like. And so we want to use this information to estimate the mean and the standard deviation. So the key word there is estimate. We can't get the sample mean or the population mean without having the actual data. And since we don't have that, we can estimate it. And they kind of give us the format for doing that. They said, first of all, let's calculate the midpoint of the bin. So from 119 to 120, what's the midpoint of that? It's 119.5. From 123 to 124, we have 123.5. That's the midpoint. Why would we use the midpoint? Why do we need the midpoint? Because we're going to say, given the midpoint and the frequency, we're going to get an estimate for the sum of the data in that range. Right? Now there's going to be error, of course, because we don't have the exact data points. But the first one says, in the range from 119 to 120, we have 1 observation. So what's the total? It's going to be 119.5. Right, we're just going to say frequency times the midpoint. That's this FM. Now, I'm actually going to pull the data down into Excel because it'll make my life easier if I do it that way. So let me just copy this. And we'll come over here. And paste it. Okay, so we've already got the frequency. And so we need the midpoint. We'll call it M. So how can I find the midpoint? Well, I could just go through and type in 119.5, 120.5, and so forth. The easier way to do it is use the average function. I'm going to average 119 and 120, and I see I get 119.5. And now if I just double click this, the bottom right corner of that cell, it will fill in everything else for me. All right, so here's the frequency, here's the midpoint, and so now what do they want? They want the frequency times the midpoint. So I'm going to come back over here and I'm going to say this is FM, frequency times the midpoint, so equals the frequency times the midpoint. And I'm going to do that for all these things as well, so I can just copy it and paste it in, or just double click on the bottom right corner, it does the autofill for me. Okay, so what have I got here? I want, let's just call this A. It's not really part A, but we'll call it A. I want X bar, and we know that X bar is the summation of the Xi's divided by N. But I don't know what the Xi's are, and so I'm going to estimate that with the summation of F times the midpoint. And then I'm going to divide that by N. Now notice I didn't put the indexes on the summations because for some reason my pen's not working and my finger's too fat to get that precision when I'm writing on this. But the summations are different. The first summation, this one here, goes from 1 up to 93 because it's looking at every single individual data point. This one only goes from 1 to 9 because I have 9 bins. And again, I've estimated the total, so like right here, the total sum of the x's in bin 1 is just going to be 119.5. That's an estimate. 361.5, that's the estimate for the 3 that I have in the second bin. So 3 times 120.5 is 361.5, and so forth. So if I sum these things up, use the sum function, I get 11,454.5. And now if I want to get the average, put it as mean. To get the mean, I'm going to just take that number and divide it by n. So I get a mean of 123.166, and I'm going to come over here and I'm going to copy and paste that right there where it says average. Okay, so that's the average, or an estimate for the average. The next thing that they're asking me for, we'll call it part B, is the sample standard deviation, S. Okay, so again, we just looked at this. We said, what is the sample standard deviation? Take the square root, this is just the formula we plug in, of the summation of xi minus x bar quantity squared divided by n minus 1. So again, all we're doing here is saying, give me an individual value for x. I've got 93 of those. Subtract the mean, which we just calculated. Square that distance, and then add those squared values up and take the average of those. So divide by n minus 1. Okay, well, again, we don't have the x values, so we're going to estimate that with the square root of the summation of f times x minus, sorry, not x, m minus x bar quantity squared, and then we're going to divide by n minus 1. And I'm given this formula here in the question, f times m minus x squared, or x bar squared. So I just need to fill in these things here, and I can do that over here in Excel very easily. I have f times m minus x bar quantity squared, and that's going to be equal to f, which is the frequency, times the quantity m minus x bar, which is a 60 quantity squared. All right, so here's a 60 down here, and so if I push enter, I get this contribution to the sum of the squares that we're looking for. And so if I copy this down, what am I going to get? I get a bunch of big numbers, don't I? Should I get big numbers? They shouldn't be that big. Why? What's the problem? Well, I'm copying the relative reference. So I need the absolute reference. So I'm going to put dollar signs here on the mean. I want the same mean every time I do this. Okay, now I'm going to copy that. You can see these numbers are a little more well behaved. And then I'm going to just take the sum of those numbers. I get 262.6 repeating. And so to get the standard deviation, I'm going to take the square root. Again, this is all stuff you could do with your calculator if you wanted. It's much easier to do it with Excel or some other software package. So I want the square root of that summation divided by the quantity n minus 1. So I get a standard deviation of 1.68. Again, this is an estimate. I'll plug it in here. And just for fun, let's take this number here, throw that one in right there. Okay, so we got the mean, standard deviation, and so let's check our work. All right, the average is correct according to this. The standard deviation is correct. But why is this not correct right here? 21.3. I used that to come up with the standard deviation. Why is it not correct? And this is the reason I'm showing you this problem. Because what didn't I do? I didn't round to 2 decimal places. Okay, you see it doesn't matter with the average, but I'm told here to round my answers to 2 decimal places. That really means I should round everything to 2 decimal places. So I'm going to come over to Excel. What's the easy way to round things? The easiest way to round is to use the function round. So round, open parenthesis, put the number that you want to round, comma, number of places you want to round to. And so I have 123.17, and that changes what I had over here to 23.386. Now, I probably should round this as well. So let me round that. Round, comma 2, and then I'll copy that and paste that in all the way down here as well. Okay, so 21.39, that's different than what I had here, 21.33. So let's replace that and then check. And we got it right now. Okay, so if you have trouble with this column especially, but you're getting the average and the standard deviation correct, that probably means you're just doing you're not rounding like they want you to. Okay, so other questions on this homework?
Okay, can we go over part B, C, part B and C?
Okay. State whether the following statement is true or false. The raw data would show us the years when the winning times were much longer than the average. Yeah, sure. Why not? I don't know. Let's try it. So what is this saying? The raw data, if we had this is just saying if you had the X values, would that show you more information? Would that show you the years when the winning times are much longer than the average? Yeah, because you'd actually see the data. So you could compare that to the average. And you'd see, you could basically calculate a z-score if you wanted. That's basically what that's saying. Now watch, I'll click check my work and I'll get it wrong. No, I got it right. Okay, what a relief. Do you think it likely that the distribution of times within each interval might not be uniform? Okay, so what is this saying? This says, given the intervals from 119 to 120, 123 to 124, for example, or 122 to 123, are those going to be uniformly distributed on those intervals? Uniformly means kind of a flat curve. Well, based on the shape of everything else, I would say probably not, because we have only one observation between 119 and 120, and then 3, and then 19, and then 30. So there's probably going to be that same sort of variability inside of each of the intervals. Although it's hard to tell, but what do I say? If I don't think it's going to be uniform, I say yes, right? Not be uniform. Yes, I think it's not going to be uniform. And so then the distribution appears to be symmetric or skewed. Looks like it's skewed, right? Because we got a handful of years up here that are lot bigger than on the other side. So I will let you guys plug that one in on your own. So other questions from homework 2? No? All right, good. Let's move on then. We're going to talk about probability. And so what is probability? When you hear the term probability, what do you think of? Chance, okay. You're going to say chance. What does chance mean? We're going to have all these different terms that really mean the same thing, and it's just going to be like circular arguments. But go ahead.
Odds of a given.
Okay, so you think of odds, all right? Think of a number between 0 and 1. And that number is supposed to tell you something about how likely an event is, right? So all those are good good ways to think of probability. The definition of probability is the study of uncertainty. So what do we mean by uncertainty? Well, this has to do with variation, right? We have a bunch of data. We know there's going to be inherent variation, randomness in the data. So uncertainty you can think of as randomness, I guess. Randomness by definition is something that can't be predicted with accuracy. So when we have data, you can think of data as being composed of, there's one way to think of it, the data is composed of information. Think of it as a signal if you're into engineering at all. So you got information in the data that is useful and relevant, that will help you make decisions, and then there is uncertainty or randomness or error that is also contained in the data. So we want to be able to explain as much of the variation in the data as we can, and then on top of that, we want to understand the randomness or the random part, how big the variation, or how much of the variation in the data comes from just random processing. So think about that when you are you're working on problems and trying to understand what's going on. Well, and I'll give you a few good examples here in just a minute of what we're talking about. Okay, so somebody mentioned odds. What's the difference between odds and probability? Is there a difference? Well, it turns out there is a difference. Usually odds are given in the form of A to B. So I think the Eagles are not favored to win the Super Bowl in 2 weeks. Is that right? By the way, the Eagles are going to the Super Bowl, in case you didn't know that.
And the riots have already begun.
The riots have already begun. Well, the bookmakers in Las Vegas and Atlantic City and wherever they are say there's some probability that the Eagles are going to win, or usually they actually give it in terms of probability of the Eagles losing. So they might say the odds the Eagles against the Eagles are 5-1, which means that the ratio of the probability for the Pats winning is 5. So their Pats are 5 times more likely to win than the Eagles if the odds are 5-1 against. So if you have the odds in favor, which is again not the way they usually do it in Las Vegas, but if you have odds in favor of some event A, then we'll say the probability of A is going to be A divided by A plus B. All right, so those are a little bit different, and you got to be careful if you quote odds as a probability, then or probability is odds, then people will take advantage of you and you'll lose money. Because usually you do that when you're trying to bet. Okay, so uncertainty is a big question we have. There's lots of people out there that want to try and explain uncertainty. Now, I asked you guys to take a look at something, and I posted in the week 3 folder an experiment on ESP. So here's the experiment. There's a guy named Clifford Pickover who's quite good mathematician, PhD from Yale, and has written like 50 books and has 450 patents, and he decided he wanted to do this experiment on ESP. All right, so he's thinking that he can write a computer program, a computer that can actually use ESP. Now, what's ESP? It's mind reading, right? So the computer is supposed to read your mind. Did anybody look at this, by the way? A few people did. What'd you think about it? Okay. What else?
I tried it multiple times and got it right.
Okay, so it got it right every time, and you're probably too busy to really dig too deep into it.
Yeah, maybe we put it together a few times, and then we analyzed it and realized why.
Okay, well, don't tell us why yet. but you did do it a few times, and it's pretty cool, isn't it?
Of course.
Yeah, I feel like at first glance, once we sit down and focus on it,
Okay, so turns out you can figure this out, but what Pickover is trying to do here is really interesting. He's trying to make you guys think that you can, or that he can, predict random things, right? But he's kind of explaining it by ESP. So here's how it works. You click on this eye, and then it brings up 6 cards. And just the whole setup of this kind of smacks at deception. But he says, okay, pick one of these cards. Just look at one card, focus on it, think about it, say it out loud. But you guys don't say it out loud, just because I don't want everybody. But do this right now, right? So you got these 6 cards, and the computer's going to read your mind. Or he's going to read your mind, or someone's going to read your mind, and they're going to say, whichever card you picked, we're going to take that one out. Okay, so just look at whichever card is yours, just the one card, stare at it, memorize it, write it down if you want to, and then come down and click on one of these 6 eyes. And it shouldn't matter which one you click on. So we'll just click on that one. Everybody have their card? And then he says, I have removed your card. Did he remove your card? Yes, he did. He removed all of the cards. None of the cards that were there before are still there. He removed all of the cards. So this is kind of a trick. I mean, you would say, well, if you're going to pick my card, why don't you just remove the 5 that are not my card? Wouldn't that be more convincing? Well, you can't do that because you'd have to randomly guess which one you picked. And yeah, so look, all these cards are going to disappear. All he does is change the suit of he changes the suit, or the color, maybe the suit too, of everything. So everything disappears. So what's he trying to do here? I mean, it's actually kind of, I think it's a joke. I'm sure it's a joke because if you look at the explanations, there's pages and pages and pages of people saying, what about Powerball lottery numbers for Washington, D.C., Maryland, and VA? You were right. You picked the right card. I chose was a king of cups. Okay. So I'm sure he went through and filtered all the comments, took out the ones where people said, you're duping us," but anyway, it's pretty amazing. Take a look at when you get a chance, and I mean, it's very, very clever. And most people, you play it 4 or 5 times, you're like, "Oh, wait a second. So what's going on here?" But is he able? I mean, he's kind of making this claim he can predict something random, right? And he's doing it through ESP, through extra sensory perception. I think that's what that stands for. So that's pretty cool. You figured that out, right? Have you ever seen emails of the kind that go like, watch Apple stock next week? It's going to go up. You ever gotten an email like that? Okay, well, just imagine that. They haven't been around for a while. And so you say, okay, Apple stock, these guys say Apple stock's going to go up. So what happens next week? It goes up. Sure enough. You're saying, wow, maybe they guessed. They go. Then you get another email from them saying, hey, did you buy Apple stock last week? Because you should have, because it went up. You made money. And so this week, we're telling you next week it's going to go up again. So if you haven't bought it yet, you might want to buy some. And you're like, I don't know. Do my own analysis. And anyway, so you look at next week, sure enough, what happens? It goes up again. And then they call it again, it goes up. And they're like, you could have made this much money if you'd listened to us. And then they say, you should sell your stock because next week it's going down. And you say, okay, we'll check and see. And sure enough, it goes down. And then it goes down. And they're calling it every single week. And after 10 weeks, they finally send you an email that says, look, here's our track record the last 12 or 10 weeks. We've gotten it right every single time. We're money managers. Why don't you give us your money and we'll manage it for you? So what do you guys think? Would you have them do that? I mean, imagine you're retired and you've got a big pile of money and you're like, I need more money, and because I don't know how long I'm going to live. And these guys seem really good. So what do you think? Would you do it? No? What if they went 20 weeks in a row? No? Why not?
Too risky to do a scam.
Too risky? Where's the risk? They got it right every single time. But you're thinking right. Yeah. Okay, so in 10 weeks, they would have had to guess 2 to the 10 times correctly. Or rather, there are 2 to the 10 choices that would have been the result of each week going up or down. So what's 2 to the 10? Anybody know? 1024. There's only one person in this class who knows that. You guys need to memorize that. You need to memorize 2 to the 1, 2 to the 2, 2 to the 4, 2 to the 3, all of those, all the way up to 2 to the 10. Why? Because it's important. So my brother, I have lots of brothers, but one of my brothers works in Washington, D.C., and he does top secret stuff, so he can't really put on his resume what he does. So he puts on his resume, consulted for such and such a company doing stuff. And on the next line it says consulted for some other company doing stuff. And so his resume's out there, and the Google people saw his resume and thought, oh, that's fun. He does stuff. We ought to interview him. So they called him up and said, hey, we want to do a phone interview with you. And he said, okay. And they said, one of the questions they asked, and from what I understand, they've kind of changed their way in which they do their interviews. But they said, if you're stranded on a desert island and you don't have a computer and you don't have a calculator, and even though you're stranded on the island, you don't have all day to figure this out, how would you come up with hold on, that's not it. How would you come up with an estimate to this number? 2 to the 24. Just a quick ballpark estimate. So how would you do that? Well, 2 raised to the 4 power, you've memorized that in the last 30 seconds, right? Because I told you need to know that. 2 to the 4 is 16. 16 times what? So this is 2 to the 4, which is 16 times 2 to the 10 times 2 to the 10. 2 to the 10 is 1024. So that's about 16 million. That's not exact because you have the 24 out here, but it's pretty close. And you can do it just like that. So it's really hard for humans to think about exponentials, powers and that sort of thing. Anyway, we've got 1024, 1,000 ways in which Apple stock could have gone up or down over 10 weeks, and they got it right every single time. The chances of doing that are 1 in 1,000. 24. Okay, so what's going on? Why would I not trust these guys? Well, first of all, they're trying to convince me that they're doing the same thing as pickover. That is, they're forecasting randomness. They're predicting randomness. Is that possible? The very definition of randomness is something that can't be predicted. Right? Now, there's going to be some information out there on the market of what Apple's, their earnings are like and their product. What they're going to release a new iPhone 27 or whatever's coming out next, and all that information is useful. But that's that's information that that you're going to want to use if you are going to go into managing money. But these guys aren't saying any of that. All they're saying is, hey, it's going up, it's going down. Listen to us, we know what we're talking about. So that's the tip off right there. So what are we saying here? How did they get it right 10 weeks in a row? Well, at week 0 or week 1, they sent out 2 million emails. And a million of the emails said it's going up, and 1 million said it's going down. And they didn't do any analysis at all. All they did was get a bunch of email addresses somewhere they bought. Somewhere you lost your email identity and now you're paying the price for it. So the second week, what do? They say, well, 1 million of these customers are gone. Forget about them. They're not going to do anything for us. So we've got 1 million. We're going to tell half of them it's going up and half of them it's going down. And then the next week, they send out 500,000 emails. 250,000 is going up, 250,000 is going down. Do that for 10 weeks, and you have 2 million that you started with divided by 1,000. You still have 2,000 people who think you know how to manage money, pick stocks, and so forth. Okay, so I'm going to show you a video. I'm going to start the video, and you can consider this part of the break that kind of illustrates what you really need in order to be able to do that. Okay, so when you're faced with things like this, you can say, wait a second, I've seen something like this before. What are the characteristics that you need, or what qualities does somebody need in order to be able to do this? Okay, so so don't think this doesn't have anything to do with what we're talking about, because it does. Okay, so we're back. I apologize about the sound. I'm not sure what happened. I restarted my computer about an hour ago, and it must have turned off the sound drivers or something. if that even makes any sense. But you should go and watch this video, How the Amazing Spider-Man 2 Should Have Ended, and you'll find out the qualifications needed in order to be able to predict randomness. And I'll just, spoiler alert, ruin this for you. At the end, Spider-Man's girlfriend dies, and he's pretty broken up about it. And he goes to the superhero cafe where Batman and Superman are sitting having coffee, and he pulls a gun on Batman, puts him in a headlock, and says to Superman, "You need to reverse time so that my girlfriend doesn't die. And if you don't, I'm going to shoot this mortal man in the face." And it's really funny. And so Superman eventually gives in and reverses time, and his girlfriend's alive, and they move to Paris and whatever. But that's what you got to have. If you can't travel through time, you can't travel faster than the speed of light, then you can't predict randomness. And it's not even really predicting randomness at that point, is it? It's going and seeing, oh, what's the result of the randomness? So if somebody tells you they can do something that hints that they know what's going to happen in the future, then you know they're lying, and don't give them your money. Because as the stock picking example, if you gave your money to those guys, they would move to the Canary Islands, and you'd never see them again, and they would just keep your money, and it would be bad for you. Okay, so again, it's important to know numbers up to 2 to the 10, and once you get to 2 to the 10, then it's just a rehash. 2 to the 4, that's 16 times. So you could say, what's 2 to the 50, for example? Well, 50 is 5, obviously 5, 0, so there's 5. So it's 1,000 raised to the 5th power, so that would be 15 zeros. Right. So going back and forth between those is good good practice. Okay, so let's say let's continue with our discussion of probability then. And a big part of what we have to do is understand what kind of information is contained in the data, and then make the best decision based on that. So if you've ever been to the county fair or the state fair, and you walk around and there's all these different booths, and they give out prizes if you can beat their game. One booth that they don't have it around too much anymore, but one booth has a hat with 3 cards in it, and one card is red on both sides, and that's that card right there. We'll just call that the red card. One card is red on one side and blue on the other side, and we'll call that the mixed card. And the last card is blue on both sides, so we'll call that the blue card. Okay, does everybody understand the setup here? So you're going to reach into the hat and you pull out a card. You pay him like $20 to play this game. And you pull out the card and you see the red side of a card. Now, the game is won by you if you can tell what's on the other side of the card without looking at it. Right? So if you use ESP, if you use your knowledge of uncertainty predictions, all those things that we said you can't do, if you figure out some way to do that, travel through time and whatever. So you're going to win if you can say what side the other side is, what color the other side is. Okay, so I want you guys to think about that, and then I want you to actually tell me what you think the probability is. All right, so if you see a red side, what's the probability that the other side is red? See how many responses we have so far. 12. Okay, so you reach in, you pull it out, you see one side's red. What's the probability the other side is red? Oops, that's not what I wanted to do. We got 24 answers so far. And whoever's saying 2/3, I don't know if you're just driving everybody else's answers on this, but okay. So those of you who said 2/3, why do you say 2/3? Nobody has an opinion as to why it's 2/3? It's the correct answer. It is 2/3. Why is it 2/3?
Well, since there's three, I guess since there's three red sides in total, they cannot even.
Had it in your head, but not anymore. Okay.
Well, if you pick a red line, it means the blue card is totally out of it, so then there's 2 chances for it to be red and 1 chance to be blue.
Okay. Right. So there's three red sides that you can pick. And how many of those red sides have blue on the other side? Just one. So the probability the other side is blue is 1 out of 3. Now you don't know which red side you picked, right? If you have the red card, there's 2 different ways. Another way to think about it is if you have the red card, there's twice as many ways to have a red face show up. Okay, so could we think about this? Yeah, oh, look at that! It jumped to 53%. Good job. It was at 39 before we revealed the answer. So we could think about this by saying, what's the probability that the second side is red given that the first side is red? All right, so if those of you who gave the right answer had good intuition, which is always useful, but let's write this down. The law of conditional probability that hopefully you saw in the videos says the probability of R2 given R1 is the probability of the intersection of R2 and R1 divided by the probability of R1. So what this means is we know that we've seen a red side. And so that changes the universe. Not everything that was possible is now possible because we've seen some event take place. So conditional on the first side coming out red, this denominator, now what's the probability of the event of interest? Okay, so how do we find the probability of the red side and R2 intersect R1? What does that mean? It means the first side we look at is red and the second side is red. What card do we have to have in order for that to happen? Got to have the red card, right? So the probability of that happening is simply 1/3. What's the probability that the first side that we look at is red? well, we've got two colors, right? We have blue and red. There's 3 red sides, there's 3 blue sides. So the classical approach probability says it should be 3 out of 6 or a half. So when you take the ratio of those things, we get 2/3. And forgive my my poor notation here. Okay, so is that clear to everybody? I know that can kind of be a tricky question. It's not, however, entirely unrelated to another question that I'm going to ask you in just a minute. But before we do that, we're going to talk about what's called Bayes' theorem. And Bayes' theorem says that if I want to know the conditional probability of A given B, we just wrote down the law of conditional probability that says this is the probability of the intersection of A and B divided by the probability of B. But we can rewrite the probability of the intersection as probability of B given A times the probability of A, and all that's divided by probability of B still. Question?
What do you mean by the intersection?
The intersection. So, like we said here, with the probability of the first side being red and the second side being red. So intersection means and. So let me write it like this. Probability of A and B. This can be written as the probability of A given B times the probability of B. If you want to think about it in terms of a picture, if I've got a Venn diagram, and here's A, and here's B, the intersection of A and B is this part right here, the part that's in both. Okay, so you can write the probability of A intersect B as the probability of B times the conditional probability. So given that I'm in B, now it's the probability of A. But you can also write it as the probability of B given A times the probability of A. So both of those hold. And all we did with Bayes' theorem is say, let's just rewrite this part here in terms of, let's solve for the probability of A given B. Okay, so what's going on is we're saying the prior probability of A taking place, in other words, unconditional probability, is multiplied by the probability of B given A divided by the probability of B. That gives us what's called the posterior probability of A. So in other words, some event B takes place, I want to update the probability of A. And if A and B are dependent on each other, then this is the way to do that. Okay? And let's look at an example. Anybody ever seen the game show Let's Make a Deal? Okay, so there's a new version of it that doesn't have this, so I'm referring back to the 70s. So the way the game show works is people dress up in crazy outfits and they try and get the attention of the game show host, and he walks up to him and says, hey, look, I've got this envelope that might be full of money, or it might be full of just scrap paper, and then I've got something in my pocket. It might be the key to a car, it might be the key to a padlock. If you can come up with 3 rubber bands and 2 paper clips in the next 30 seconds, I'll let you pick between the envelope and what's in my pocket. And so they scramble through their purse, their pocket, and they come prepared for these sorts of things. And they come up with the stuff, and then they say, okay, I want what's in the envelope, and they say, okay, there's a pile of money in the envelope, and so they're kind of still in the game. And towards the end of the game, sometimes they would offer this opportunity where there are, say, 3 different curtains or doors, and they can trade whatever they earned this far to play this game. And behind one of the doors is a fabulous prize, like an all-expense-paid trip around the world, or a pile of money, or a Ferrari, or something like that. And behind the other 2 doors, there's a donkey. And so Monty Hall says, look, pick whichever door you want. So who wants to play? Up here. So you pick door number 2. All right. Then Monty Hall, what does he do? He opens up one of the doors and shows what? A donkey. And then he says, then what does he say? He says, unless you live in Lancaster County, you don't want the donkey. Because it's, you're going to have to find somewhere to put it and feed it, and it's not worth anything to you. So you really don't want a donkey. But you've got the choice now. You can either stay with your initial pick, or you can switch to the other unopened door. So what's the best strategy here? Should you switch? Should you stay? Does it matter? In other words, if you say it doesn't matter, what are you saying? Well, chances are 50-50, and I can flip a coin to this side. How many people are here today? So I got there. I just counted 40 people. I've only got 25 responses. I'll let the 10 of you that haven't responded yet slide, but I'm going to ask you another question a little bit later that you're all going to have to answer. So, okay, let's just start at the bottom here. Doesn't matter. Who says it doesn't matter? Why doesn't it matter?
Once you take the one doorway, it's 50-50.
Okay, because once there's only 2 doors left, then it's 50-50. And it looks like 34% of you said agreed with that. Those of you that said to stay, why did you say to stay? I'll venture a guess then, if you guys don't want to own up to your opinions. You said, look, it doesn't matter, it's 50-50, but I'm going to go with my initial impression. Right? Okay. So those of you that said to switch, and that's 45% of you, why did you say to switch?
Well, in the beginning, you have a 2/3 chance of getting it wrong. So when you take out one of the doors, you're still 2/3 likely that you're wrong.
Okay.
So when you switch, it's like 1/3 chance that you're wrong rather than 2/3.
Okay. So your chances of winning if you switch are what?
2/3.
2/3. All right. You want to add into that?
First, it was a 1/3 chance, so then by switching, it therefore makes it a 2/3 chance to win.
Okay. Why was it 1/3 in the first place? Because there's only one prize, right? And there's 3 doors to choose from. Okay, so this can kind of be a sticky problem, but I think it's really important to understand what's going on with this problem in terms of decision making and probability and information. So what information do we have? And what we do with the information that we have is vitally important. So what information do we have? What's the first piece of information?
We have something big in one door and two donkeys on the other two.
Okay, so we know there's a donkey, or sorry, two donkeys and a big prize, okay? And we know that he's only going to open up door number, or whatever door has a donkey behind it. Okay, so what's the next piece of information we get? You picked a door, right? You picked door number 2. That's the only piece of information we have up to that point, other than how the game's set up. So you picked door number 2, and the game show host then opens another door. But is it just any other door that he opens? No, in this case it's door number 3. So we've got this information. We need to use the information to the best of our ability. So look at the doors and say, well, there's just 2 doors now. That actually throws out the information that we have, a lot of the information. So if you said the probability is 1/3 that I initially picked the money, then you're right. And then if you said, well, now there's only 2 doors, so the probability is 1/2. That's not true. That's not right. Unless you randomly choose between those doors. So this is very, very interesting, because if you think the probability is 1/2 that you're going to win, and you randomly choose between the 2 doors that are left, guess what? You win half the time. So it is 1/2. But that's not the best strategy. The best strategy, using the information, all the information you have to the best of your ability, would be to switch. And the reason for that is, what's the probability you originally pick a donkey? Like you said, 2/3. If you pick a donkey in the first place, you're not going to switch to a donkey. You're going to switch to the money. If you pick the money in the first place and you switch, you're not going to switch to money, right? You're going to switch to a donkey. The probability you pick a donkey or the money in the first place is 1/3. So if your strategy is to switch, you're going to win 2/3 of the time if you switch, 1/3 of the time if you stay. If you average 2/3 and 1/3, what do you get? 1/2, which is the probability you win if you randomly stay or switch. So if your strategy is to switch, you're going to be better off. Okay, so oftentimes we're faced with questions that we get information for, and then we totally botch the analysis. We say, okay, I don't know, it doesn't matter, let's just randomly pick. And you get, in the long run, what you think you're getting, but you're not as well off. So what do you want to do? Switch or stay? You want to switch? All right, well, sorry, you lost. Now, I'll tell you, before I started any of this, I said I'm going to put money behind door number 2. So what is that? We just went through this and said the best thing to do is to switch. You should always switch. What is that? That's the signal. That's the best use of the information that we have. But what is there always in addition to that? Randomness. And that we can't predict. Okay? So if you're having trouble understanding this, and I know it's not necessarily the easiest thing in the world to wrap your head around, come over to this Let's Make a Deal applet. Don't open it in Chrome or anything new. Go to something old that still uses JavaScript. And say run this time. Run. And you can play the game as many times as you want. and it will keep track of the times that you win when you switch and when you don't switch. So here I pick 1. Monty Hall opens door number 2. I said to switch. Looks like I won that time, and I didn't win that time. I didn't win that time. I didn't win that time, but I won that time, and I won that time. I won that time. And it's really fun. If you've ever played with like a Nintendo or a Wii or a PlayStation, anybody ever done that? You can get into this nice little rhythm, and it's just 3 clicks. Move your cursor, move the mouse, and I'm just gonna play this like how many times? 6 more times. Okay, it says in 30, oh, this is not a good result. You can't read it, but it says 31 games in which I have switched, I won 16 times. That's actually less than a half, isn't it? So that doesn't really help my case. But playing it 31 times is not enough. I'm not going to play it again, but I'll let you guys do this on your own. But this is something called a computer simulation. This is the frequentist approach to probability. It says let's just do the experiment over and over and over and over again. And if we do it enough times, then the probability of success for the event we're interested in will converge to the sum of times that we get it right. So I'm going to play it a bunch of times where I don't switch. This is even faster. I don't know if it's more fun, but it's faster. There's 19, 20, just to make sure you don't think it has to do with what door you pick. Alright, so it says in 32 games, oh boy, this is bad. 32 games in which I have not switched, I won 15 times. So play this a bunch of times, like do it 100 times, because there must have something wrong with my JavaScript number generator or something. I don't know what's going on. Usually it does do that. But oftentimes you're faced with problems like this that are hard to understand, and you think you understand it and make your decisions based on it, but it turns out that computer software or simulation can help you understand better what's going on. So again, 30 times is obviously not enough to demonstrate it this time, but you could actually come over here and write down the probability of winning when you switch and when you don't switch. Okay, so we're going to say M is the event that they open door 3. Okay? Is that the door we open? That's the door we open, right? We showed a donkey behind door number 3. We could say, what's the conditional probability then that M happens, or door 3 is opened, given that the prize is behind door number 1? So think about this. And also given that you pick door number 2. Okay, so if the money's behind door number 1, you pick door number 2, what's the probability that door number 3 is going to be open? Well, if you don't pick the money the first time, then Monty Hall only has one. Sorry, if you do pick, if you pick the money the first time, Monty Hall has 2 doors he can choose to open, right? But that's not the situation here. You pick door number 2, and no, sorry, that is the situation here. You pick door number 2. The money was behind door number 2. So what's the probability he opened door number 3? Should be a half. Right? You had 2 doors to choose from. Oh no, I'm sorry. Conditional on the money being behind door number 1. I messed that up. Let me erase this. So we're saying conditional on the money being behind door number 1, you pick door number 2, he has to open door number 3. So that's 100%. Probability that he opens door number 3 given that the money's behind door number 2 and you pick door number 2 is what? 50%. You can either open door number 1 or door number 2. And the probability that he opens door number 3 given money's behind door number 3 and that you pick door number 2 is 0. He's never going to reveal where the money is. Okay, so Bayes' theorem says we can calculate the probability that, see, we want the money's behind door number 1 given that he opened door number 3, and this is just going to be the probability that he opens door number 3 given the money's behind door number 1 times the prior probability of the money's behind door number 1 divided by the probability that he opens door number 3. Okay, so what's the probability that he opens door number 3? That's the probability of door 3 given 1 times the probability of door 1 plus the probability of opening door 3 given door 2 times the probability of door 2 plus the probability of m given 3 and the probability of 3. And one of those things is 0. It's the last one, isn't it? M given 3 is 0. So then we get 1 times a third plus a half times a third. So we have a third plus a sixth. That's equal to a half. All right. So given you pick door number 2, which there's a 50% chance that he's going to open door number 3. Okay, so that needs to be divided by this numerator. So again, we got the probability of 1 given m is p of m given 1, which is 1. So 1 times the third divided by a half is 2/3. So probability that money's behind door number 1 given that he opens door number 3 and that you picked door number 2 initially is 2/3. Okay, so we, if our appeal to the simulation doesn't convince us, Bayes' theorem here should convince us as well. I will post these slides too after class.
Alright, so that was first little bit. Can you just explain before that?
This part here.
Yeah, something like
So this is Bayes' theorem right here. So this says, what's the probability that the money's behind door number 1 given m? And we said m is the door that Monty Hall opens. So he opens door number 3 in our situation, right? So given that he opens door number 3, and you should also say and that door number 2 was the initial pick, what's the probability that the money's behind door number 1? And we can calculate that by saying, well, what's the probability that he opens door number 3 and the money's behind door number 1 times the prior probability, so that's the prior probability right there, the prior probability that the money's behind door number 1. So the prior probability says unconditional on any information, what's the probability that the event takes place? And so we'd say, what's the probability the money's behind door number 1? If we don't have any information, that's a third. All right, and then we're going to divide that by the probability that he opens door number 3.
So the probability of 1, probability of 2, and 3, are they all 1/3?
P1, yeah, sorry, P1, P2, and P3 are all a third. Yep. That's just saying unconditional on anything. What's the probability that money's behind door number 1, money's behind door number 2, money's behind door number 3. Okay, so there's lots of applications of Bayes' theorem, and one of the questions that was asked at the beginning of class today for the next homework is one of those questions. So, so think about Bayes' theorem and how to apply it. I think it's like a biometric scanner to get into the NSA or something like that, and there's a certain rate at which it lets people in when they shouldn't get in, and there's a certain rate at which it doesn't let people in that should get in, and so you have a prior probability given as well, and then something happens, they don't get in, and so you want to update the probability that that they should be getting in or not, that they're authorized. So that's one example. Another example is like a doctor's visit. If you had there was a rare disease out there, like 1 in a million, you go to your doctor and he says, I think you got this disease. And you say, well, why do you think that? And he says, I just think it. And you say, okay, well, let's take a test. Is there a test we can do? And he says, yeah, there's a test, and it's 99% accurate if you have the disease. And if you don't have the disease, it's 98% accurate. And you say, okay, get the test done. The test comes back positive. And he says, look, you got the disease. Test is positive. What do you guys think about that? Is the math been done right? Turns out there's still only about a 5% chance that you've got the disease in that scenario. But that's an application of Bayes' theorem, and so we're almost out of time. So I'm not gonna go into that in any more detail. Instead, we're going to talk about counting. And there's lots of interesting things with counting. You all thought that you knew how to count already just by taking whatever integer you're at and adding another integer to it, but there's more to it. There's something called the product rule, which says if I've got a process that needs to be performed and there are a certain number of tasks or sub-processes, and I want to count the total number of ways that I can perform the process, all I have to do is count the number of ways I can do each step and multiply those together. So for example, if you're going to go out to dinner with your friends on Friday night, and you go to a place that has sandwiches, and you say, how many sandwiches are there that I could buy? Let's say, just for the sake of argument, that there's 10 sandwiches. And then you said, okay, I want a side. So many sides are there? And they've got a whole list of them. And there's there's mac and cheese, and there's French fries, and there's coleslaw, and all those things. There's 10 of those. And then what do you need? You need a drink. And so you say there's 7 drinks. And of course, these are all small numbers because most restaurants have lots of variations. For example, with the sandwich, you could say there's 8 different toppings I could put on the sandwich. So how many ways can I choose my sandwich? Well, that would be 2 to the 8th, or 256 different ways. So I could multiply that in there as well. I'm not going to put that in right now though. And then finally, I'm going to say dessert. For dessert, let's say there's 4 different options. So how many different meals could I get if I got one of each of these things? We'll just multiply all that together, and you get, what's that number? 2,800 different meals. Now again, if you multiply that by 256, the number of ways you can choose your sandwich, and then with your drink, what can you do with your drink? You can either have small, medium, large. You can have ice or no ice. Multiply all that stuff out. These numbers grow very quickly. But even with 2,800 different dinners that you could get, it might take you a while to figure out what you want. Right? There's a lot of possibilities. Does the roast beef go with potato wedges and chocolate fondant. I don't know. If it does, great. If it doesn't, then you got to figure something else out. So, you know, they call it fast food, but typically you're looking at hundreds of thousands of options when you go to a fast food place. And so, you know, be patient with people. Permutations are a simple continuation or specialization of that product rule. For permutations, you would say, how many objects do we have? Let's say we've got 6 different objects, six people, and we want to select 3 of those people to be a class presidency. Right? So you got a class with 6 people in it. You would say, how many ways can I pick the first person? There's 6, and then you can't be the president and the vice president, so then there's 5 ways to pick a vice president, and then there's 4 ways to pick a secretary. So this says if Jeff is the president and Doug is the vice president and Sally is the secretary, that's a different presidency than if Sally's the president and Jeff's the vice president and Doug's the secretary. All right, so order matters if we're dealing with permutations. But what's really going on here is we're breaking the group up into two groups. And so we would say there's 3, 2, 1 ways to select the next 3. But we don't care about the order of the 3 that are not in the presidency. So order matters when we're dealing with permutations in the group that we're selecting. The group we're not selecting doesn't matter. So we could write this as 6 factorial divided by 3 factorial. Okay, so this is something that's very useful, and in fact I'm going to ask you a question that has to do with this. So we have 40 people in the room, 41 counting me. What's the probability that at least 2 of us have the same birthday? And you would use the permutations to calculate that, and we'll see if we get a chance to write down the formula. But I don't want you to calculate it. I just want you to tell me what you think. Yeah. So 40 people, what's the probability at least 2 of us have the same birthday? And you know, just imagine you're out on the street and somebody says, hey, I'll make you a bet real quick. If you know, were those 2 of those 10 people over there, do you want to bet me that 2 of them have the same birthday? Or of those 40 people over there, would you bet me? We got 16 so far. Let's see what kind of results we're getting. 0.1. So 10%, 50%. 20%. All right, let's look at the results here. Okay, so we've got 10%. We got 0.2%, 0.2, 0.5, 0.6, and then more low percentages. There's a few high, 94%, 90%, 0.9, 0.89. Okay, so anybody who says like less than, probably less than 10% might be interested in this offer. I mentioned someone might say, hey, what do you want to bet? So I'm going to ask you what if you'd like to take this bet. Here's the bet. I think that at least 2 people in the classroom have the same birthday. That's day and month and day, not year. And I'm convinced that that's the case. So if you bet against me, then you're betting that no one in the room has the same birthday as anybody else. Now, if you're right, you don't have to come to class again. You'll get an A in this class. You can tell all your friends, hey, I got an A in statistics and I did it in the 3rd week. That's how smart I am. It was like, easy. You don't, you're all done with stat201. If I'm right and you lose the bet, almost exactly the same thing happens, except for you don't get the bragging rights. Instead, you can tell your friends that you flunked out in the 3rd week. So you either get an A if you're right, or you get an F if I'm right. Okay, so who wants to take that bet? 1. Well, I mean, if this is you, if you think the probability is 0.2%, that's pretty. I mean, that's a pretty easy bet. Okay, so just 1, or is there 2? All right, so this next question I'm going to ask you is very important that everybody answers.
I take it back.
All right, what is your birthday? Please do month, day format. And this time I need 40 responses, and this is an easy question for most of you. Should be, anyway. And I'll just tell you right now that in my last class, 5 people failed. All right, we got 35. We need 5 more, 4 more. Maybe I miscounted. Anybody still not submitted theirs yet? 39. All right, there's 40. So, 41. All right. So let's look at the response history. Oh, and by the way, my birthday is August 27th. I didn't submit it, but before I've looked at all these, you'll be able to verify that. Oh, who did that? Now we got to figure out. So we got April. Where? Who? What? April 12th. Raise your hand. Did someone just fix it? Oh, it is the same user. Okay, so we should need to. January 29th. Raise your hands. 1, 2. Oh my goodness, you're even on the same row. Did you guys know that? Do you have the same birthday? Isn't that just? I mean, that's astonishing, isn't it? It's crazy. Are there any other pairs? Usually there's, with this many people, there's a couple. May 12th. That's my wife's birthday. Does that count for anything? So there was just 2 this time, huh? Except for that person who put theirs in twice. Or, no wait, was there any August? My birthday's not there. December 5th, there was a December 5th, wasn't there? December 5th, is that the same user? Okay. So they fixed it? Okay. Alright, so let me just show you one other thing real quickly. If you want to know what the actual probability is, go over here to this link in the week 3 folder and click on birthdays and say how many people do we have, including myself. There were 41. So with 41 people, the probability is 90%, 90.31%. So that's why I was willing to make that bet. You should come see me after we need to talk. but if you don't believe this, you can actually do a simulation here. So click on X1, and it will randomly sample 41 birthdays. And if you want to do 5,000 at a time, you can do 5,000 at a time. So we will see you guys next week, and we'll talk about Chapter 6 stuff, answer questions on Homework 3, and yeah, so we'll see you then.